We're going to talk about how springs, the forces that springs exert on objects. All right, and I brought a few springs to use in class today. So springs are a little bit different than anything we've dealt with before because the amount of force that a spring applies to some object it's variable. And if you think about that, that sort of makes a little bit of sense, right? I mean, you've got a spring here. This spring, if I pull it a little bit, it's not very hard. If I pull it more, it gets harder. And then, once I get out here, it's like, oh, okay, now I'm really working hard. All right, so as I pull this thing, if I stretch it out more and more, it gets harder and harder to pull a little bit further. So if I want to write an equation that represents that, I need to define a few things. I need to define a few quantities. So let me draw a few springs here. All right, here's a spring. It's attached to a mass. And I'm going to call this spring unstretched. All right, in that case, when the spring is just sitting there, it's unstretched, what force do you think it applies to any object that's attached to it? Right. It's not applying any force in this case. However, if I take that spring and I stretch it out a little bit, so this is the stretched case, well, now it's applying a force. So the force is not zero. And the force that it's applying is, back to the left in this case. Right? It wants to go back to its unstretched position. So this is the force. And it's not equal to zero. Conversely, if I take that spring and I compress it, like so, sorry, there should be a force not equal to zero. Once again, the force is not equal to zero. And in this case, the force is going to point to the right. It wants to go back to its equilibrium position, where it's not applying a force. So there's something then that I need to define here in order to quantify what the strength of the force is. All right, any guesses how I might relate the force to, or how I might define the force, the magnitude of the force? All right, that's pretty close. It is proportional to the distance. So in that distance, by distance, what I mean is it's proportional to the displacement of the object from the unstretched position. All right, so in this stretch case, this is delta x, this distance here to the right, or this displacement to the right. In this case here of the compressed example, this is my displacement. All right, so it's proportional to that. You mentioned a constant. It's not plus a constant. It's times a constant. All right, so I'm writing it like this, which maybe is a little bit complex. I've written the magnitude of the force is equal to minus k times delta x. All right, all this says is that the force is equal to some constant times the distance from the unstretched position. All right, so some constant times the distance from the unstretched position. And that negative sign, that basically tells you that the force is opposing the direction of the stretch. Right? So anytime you stretch a string, like in this case to the right, the force is going to act to the left. If I compress the string to the left, the force is going to act to push it back to the right. All right, so that minus sign is sort of a reminder. All right. Most of the time, you'll write this equation. F equals minus kx. However you want to write it, this has a special name. It's called Hooke's law. Point out names because these are things that pop up on standardized exams, although they're not terribly important for you guys. If you're taking the MCAT, they might refer to Hooke's law, so you should be aware of it. I don't know this. Who here is considering taking the MCAT? Anybody? Lots of you. I've taught a MCAT review course for physics. I really feel sorry for you guys. They test on everything. It's like all of physics you must know. It's very hard to cover that stuff in 2 semesters. Okay, so that's the force due to a spring. Just like when we were dealing with force due to friction, it had some value that we could evaluate, mu sub k times the normal force. The spring's the same way. Now we just have another value that we can evaluate. We could plug into an example, and you can get some sort of force. So let's take a look at this and apply it in an example. We'll go back. We'll do some more inclined planes because you guys love them. All right, so here's our plane. We're going to put a very oddly shaped 20 kilogram mass on the plane. And we're going to attach that guy to a spring like so. All right, so the spring is supporting the mass. The mass is not accelerating. So I want to know if there's no friction. And the spring is compressed by 0.2 meters. What is k? All right, what is that constant that went in front of x? Okay, so what we're dealing with here is another Newton's second law problem. The first thing to do whenever I'm doing Newton's second law, whenever I'm looking into forces, is to draw a free body diagram. So this has the force of gravity acting on it. There's a normal force, and there's a force due to the spring. I'll draw like that. There's no friction. It's not accelerating. All right, let's do it. Let's make the x direction go this way, and then the y direction go this way. I was trying to do it both ways. Okay, sorry. Now we've got a rotated coordinate system. Now the normal force is not going to apply if we sum the forces in the x direction this time. This will make life a little bit easier anyway. So if I do that now, what I have is, let's go with orange. Gravity is applying in the x and y directions. So I have, this is the y component of the gravity. This term right here is the x component of gravity. So gravity is pulling the mass downwards, or to the right in the x direction. So I have a force due to gravity in the x. And the spring is opposing that motion up and to the left in the negative x direction. And that's equal to 0. Okay? Now once again, I'm going to evaluate the force due to the spring. I've included the direction in my drawing, so I don't need to include this negative sign. Sometimes it's good to think of this as just a reminder that the spring is going to oppose whichever direction it's stretched or compressed. So Fg sub x, the x component of gravity, well, that's just the mass times gravity. I know this angle because I'm going to give it to you. Let's see, I went with 20 degrees. So that angle is 20. I need then, since this angle is 20, I need to know the cosine. Mg times the cosine of 20. I'm sorry, that's not 20. Don't get mad at me yet. I know 2 mistakes in a row. Oh my goodness. That's not 20 because this angle is 20 over here. That's 20. So again, because if I look at this, I rotate my x-axis up to my new axis, like here. So if I find the angle between my original y-axis, which is down, and my new y-axis, that's got to be 20 degrees. Right. So that means that this angle is 20. So then I'm going to use this sign to get my x component. All right, so find find your old axis and your new axis. So my old axis was my old y-axis was right here. My new y-axis is right here. The angle between them is 20. The reason that this was not 20, this was my old my old y-axis. This is my new x-axis. I got to find the angle between the same axis, the x or the y. So this is the old y-axis. This is the new y-axis. That's 20. Yep, absolutely. Could have done a cosine of 70. That's fine. All right, so mg sine of 20, that's the x component of gravity, minus the force due to the spring. That's just k times delta x. I'm given delta x right here. That's equal to 0. So I'm after k. That's equal to, if I solve for k, mg sine of 20 divided by delta x. So I plug in my numbers. I know that I've got a 20 kilogram mass. G is 9.8 meters per second squared times the sine of 20 degrees divided by 0.2 meters. And if you solve for that, you get 335 Newton meters, I believe. I'm sorry, 335 newtons per meter. All right, so again, just the Newton's second law problem, just like we've done before. And the picture is very similar to the ones we've done before when there's friction involved. All we did is instead of having friction, we have the spring force. It's just something new, something slightly different. But we apply it in the exact same way. Now, I haven't talked about this K thing. All right, I haven't mentioned anything about that other than saying it's just some constant. So K is known as the spring constant. And all that K tells you is basically how stiff the spring is. How hard is it to stretch the spring? Or in other words, for a given force, if you have a small K value, then your x distance has to be large. Right? If you use another spring that has a very large K value, then your x has to be small. The x displacement will be small. So I brought 2 different springs right here that are very hard to see. All right, so I've got 2 different devices right here, and they both have springs in them. You can sort of see. They're both the same length initially. All right, so if I put this up here so that I'm not holding these things, hang the springs. All right, so we've got 2 springs that are the same length. I put the 500 gram mass on one of them. It stretches yay far. All right, and you can see that this is measures the mass. So I get 5. It goes to 5. This is actually in newtons. So 5 newtons. This is 500 grams. So the force is the weight of this mass is almost 500 or 5 newtons. I'm sorry, 50 newtons. But so it stretches that far. Okay, that's what we're after here. So, a couple of centimeters. If I put it on this spring, all right, it stretches down to here. So we had the 5 is right here. So that far on the spring on the left, this far on the spring on the right. So tell me which spring has a larger spring constant?
On the left.
The one on your left. So this guy. My left? Your left. Okay. So this guy, because in order to get the spring, when I put the weight on there, it didn't stretch as far. So if it didn't stretch as far, for the same force, it went a smaller distance, which means K had to be larger. Okay? Another way to think of it is it's much harder for me to pull this spring than it is for me to pull this spring. So this is a stiffer spring. The one with the higher K value is a stiffer spring. Yeah, Chiefs.
So that's a smaller displacement?
This one had a smaller displacement, correct.
So
a bigger K. So a bigger, a bigger K. All right, that's the only reason I brought these things. Okay, so that's all there is to it when we're dealing with springs. And so the last aspect, the last thing we're going to do when talking about forces is to talk about something slightly different. And that is to apply everything we've learned so far to motion in a circle. All right, so we've been dealing with all these problems where we have masses sliding on blocks and pulleys and things like that, but all of our motion has been in a straight line. All right? But now we want to take a look at, maybe one step further in the complexity scale, on the complexity scale. So we know that if there's no force acting on an object, well then you have no acceleration, right? If there's no force, there's no acceleration, so you have constant speed. In addition to constant speed, what else do you have if there's no acceleration? What's that there? Okay, so constant velocity implies constant speed, and what else? What? I can't hear you. There's a fan.
So we have
Constant velocity, you have a constant speed and a constant.
well, you said that we don't want this with the
Okay. A constant.
I'm saying something you wanted to go down.
Okay. So you said velocity is correct, and I just wanted to break it down into these two parts. So a constant velocity also implies a constant speed and a constant direction. Now it's going to get really warm in here. Okay, so constant direction. If we're moving in a circle, though, our direction is changing. So we have to look at something a little bit more complicated then. But it's nothing new, nothing that we haven't dealt with before. So in order to change direction, if you have an object that's changing direction, you have to accelerate. Whoa. And if you're accelerating, then there must be a net force acting on the object. So motion in a circle implies that there is a force acting on the object of interest. Okay? In the case of circular motion, we do have a force, and the force is constant. We are. Huh? I just wrote it again. So I just wanted to write it again. So in the case of circular motion, which is what we're talking about, there is a constant force that's applied to the object. All right? So if I have an object that is right here, and it's traveling with a velocity in that direction, in order to get this thing to move in a circle, I have to apply a force. I want it to change a direction. What direction do I have to apply the force to get this thing to turn? Okay, that's good. There are many different directions. Which direction in particular? Towards what? Point it towards the center of the circle. In other words, I need to apply a force perpendicular to the direction of motion. All right, so a constant force is applied to the object perpendicular. It has to be perpendicular. And let me explain why. All right, so here I have a drawing. I kind of didn't leave myself very much room. Can I move it? I can't move it. Magic. All right. So here I have an object. It's moving it's moving up in my picture. I've applied a force to the right. That means it's going to change direction. But if you remember back to kinematics, what does that mean about the speed of that object? All right, if I apply a force, if I cause this thing, so if I apply a force to the right, which direction is it going to accelerate in? Hmm? Who says upper right? So like this direction? All right. Who says up? Who says what else? What else is there? Right. All right. This is extremely important. If you don't get this right, you're going to not do very well on your exam. Newton's second law. If there is a force, or if there is a net force acting on an object, then it must accelerate in the same exact direction as that net force. So if I'm applying a force to this ball, that's the only force, it better accelerate in that direction. Now, this is so obvious if you just think about it. If I push this spring across the table, if I push it in this direction, it's going to accelerate in that direction.
So it'll accelerate in that direction, but its actual trajectory would be up or right?
Its motion is going to change, right? If it's so all of its velocity initially is in the y direction, right? But now I'm accelerating it in the x direction. So it's going to start to turn. So what's going to happen is it's going to start to turn. So here's the initial velocity, but it's going to start to accelerate and it's going to curve. Okay? At every point along this curve, though, if I want this thing to go in a circle, I need to apply a force always perpendicular to the direction of motion. So if I take a snapshot right here, the force will be directed down and to the right a little bit. So imagine that this force vector is changing, and then when the ball or the object gets up here, now the force is going to be directed straight downwards. And the ball will accelerate in the same direction. And if I complete this picture, it's going to keep going, and it'll get here, where the force is directed to the right in the same direction as the acceleration. And then eventually it'll get back to where it started. Sorry, it's a squash circle. But this is supposed to be a perfect circle. Okay? Circular motion implies that the force is always perpendicular to the direction of motion, and the force is constant. If the force weren't constant, so let's say that the force got larger and larger as I curved up here, how would that change the motion? Would it curve less or would it curve more? All right, it would curve harder. So it would start off with a gentle curve, and then it would curve harder and 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 harder, and you'd end up getting these spirals. It's some sort of a spiral. But if the force is constant, you get a nice circle, and you end up where you started. All right, so in circular motion, we have a force that's applied perpendicular to the direction of motion, and it's constant. Now, as it turns out, oh, sorry, Shane.
Is there a reason you do the acceleration vectors longer?
Just to make them different. They don't have, I mean, you know, it's dependent on the mass. The magnitude of the acceleration is dependent on the mass, how it relates to the magnitude of the force. So just so that they're different. Okay, so this acceleration, this A thing that I've written, when we're dealing with circular motion, when we're dealing with motion that's curving, this has a special name. And we call it in centripetal acceleration. Okay? What we mean by centripetal acceleration is any acceleration that occurs perpendicular to the direction of motion. All right? So when we're dealing with motion that does not go in a straight line, that curves, we tend to break up the total acceleration vector into two components. The acceleration, centripetal acceleration, and then also the centripetal, the parallel acceleration, which we don't really have a special name for. That's just the acceleration that occurs in the direction of motion. Okay? When we're dealing with circular motion, that guy is 0. So for circular motion, the perpendicular acceleration is 0. Because centripetal acceleration is so sort of important, it has its own equation. And I'm not going to bother deriving it. I'm just going to write it down. So you can calculate the magnitude of the centripetal acceleration if you know the object's velocity and the radius of the circle. Not vector. Okay? So it's equal to v squared divided by r. That's centripetal acceleration. I guess I should put magnitudes around there. So the speed squared divided by the radius of the circle. That'll tell you the centripetal acceleration of an object. Now before we go off and do some examples here, I just want to point out that I said centripetal, not centrifugal. Who's heard of centrifugal force? All right, so most people hear of centrifugal force because when you're in a car and you turn, you feel this centrifugal force that's trying to spit you out the side. All right? It is incorrect to say that there is no such thing as centrifugal force, which is many a high school level physics teacher might say. There is such a thing as centrifugal force, but it's much more complicated than anything we want to deal with here. It has to deal with non-inertial coordinate systems, accelerating coordinate reference frames, and stuff like that that you guys don't care about. All right, so this is centripetal, not centrifugal. If you want to learn about centrifugal force, then we can talk in my office all about, imagining yourself in a rotating, accelerating coordinate system. All right, but we're dealing with centripetal. If in your book, and I'm not going to really harp on this too much, they'll refer to this force, the force that's perpendicular to the direction of motion, the force that causes a curve to be centripetal force. Fine, whatever, you can think like that. I don't think it's that important to make the designation because there's nothing really that we can say about the force other than it's perpendicular to the direction of motion. But I just want to point out that they might say that in the book. All right. Okay, so when we come back, we'll deal with a little bit of an example. Let's have a quick break, and we'll see you in about 10 minutes. Hey.
I just have a couple of quick questions about the exam, if you don't mind.
Sure.
I personally like to use a lot of scrap paper when I work on stuff, and so I don't know, would you have scrap paper available? Does it all have to be
Yeah,
on
I'll bring some blank sheets,
Okay.
and you can use as much as you want. I just ask that whatever you submit to me
Yeah,
be organized so that
Oh,
I
yeah.
can follow your logic.
sure. Okay,
Otherwise, it might be difficult to assign you partial credit.
sure. And then the last question I had was, I don't know if this is something that you want to say, but do you know like the relative, and I'm studying the relative importance of each chapter, like chapter 1 obviously it was about, what is a unit, right? Whereas we spend a lot more time on
I'll
Newton's
try to-
laws and two-dimensional kinematics.
Yeah, so I'll talk about that tomorrow, but it'll
Oh.
probably be, at least a couple problems on Newton's laws. Probably one 1D kinematics problem, one 2D kinematics problem, and maybe like a combination kinematics force problem or something like that.
Okay, well, I'll just wait till tomorrow to ask you. Okay, thanks.
We have some questions on the right side.
Okay.
Number 9, we just we don't know how we're to start, I guess. It starts right here.
Mm-hmm.
It's about the shape.
Okay, the scale, right. Okay.
Where would be a suggested starting point? Because we thought it was going to be similar to the one the scale problem we did in class, but couldn't find a relationship.
Right, so, just remember that you're really looking at the scale, So you're applying Newton's second law to the scale, and you're really sort of solving for, I mean, the force, the reading on the scale is the normal force, okay? So you have that, and with that in mind, you can do a Newton's second law. Yeah, so what you're really doing is you're solving for the normal force on the scale, but then you're applying that to the person. So that normal force is acting on the person because of Newton's third law. So you have an equal and opposite force on the person. So that normal force, that's, like I said, that's the 81.65. That's what the scale reads, so that's the, and then the equal and opposite to that is what's applying on the person, which is balanced by gravity and any acceleration. So you've got this equation written down correctly. And so what you need to do is you know the mass of the person. You know the initial weight of the person. So you know the initial weight of the person. You know the new weight of the person. The only way that those two things can be different is if the person's accelerating. So you have that written down so you can get an acceleration. So I'm not sure.
I thought the mass was the new weight. I used that as the new weight, so that's the weight.
105.
Into kilograms. The 230. He reads 233 pounds when
Okay.
the ship is
Yes.
a storm, and then 140 pounds when the ship is like bombing down. Like two different.
Right, so what you have to do is you're basically calculating two accelerations, one for this one and one for that one.
Okay.
And comparing, and then this is the constant between the two. That's the force due to gravity. That's the weight, so that's this term.
Okay.
These two, those are the normal forces. Those are those forces that are read by the scale.
Okay.
So you take the difference and you're left with the mass times acceleration.
Okay.
You could find the mass of the person, but you don't need to, because that's not true. You do need to find the mass because you need it here. So you have to find the mass of the person. You could use, we do that with this number. So
Weight divided by gravity.
yeah, exactly.
So how do you know that the normal force is what, like the weight is, I guess?
This is that's
The new weight.
the new weight, right? So draw the free body diagram of the person.
I guess I do have the scale, but the person, so they have gravity going down.
So draw it.
Okay.
So this is your missing step. You don't have a free body diagram, right?
Well,
You have a little miniature one.
Okay.
You have one on the scale. That's correct.
So the force of gravity going down on the person, the force of the scale, so the normal force,
Right.
which is the scale.
So the reason you have the scale here, which is fine, and that's the point of that is to recognize that the normal force acting on a scale, because you have a measurement on the scale. So that tells me that that's a force that's being applied to the scale, not the person.
Right.
But then you should recognize that when you draw this free body diagram, that normal force, that's what it's reading. That's applying to that has an equal and opposite force that's supporting the person. So yeah, the reading is applying to the scale, but then the equal and opposite of that is applying to the person.
Okay.
So the free body diagram for the person includes that number. That's the normal force.
Okay. All right.
So the weight of the person is the normal force acting on the scale. Is that right?
The measured weight of the person.
Okay.
Yeah, the true weight of the person, m times g, is just m times g. So the weight that the scale shows, which is called apparent weight, the weight that you feel because you're accelerating, that's what the normal force on the scale.
So weight is calculated as mass times gravity? It's the same as the force of gravity?
That's what I said like a week ago. Weight, force due to gravity, these the same terms.
Okay. I feel like I didn't listen like that.
No, that's okay, because in these problems we kind of talk about weight has this weird mixed meaning. So that's why in the book and other places you hear that be the apparent weight. It's not the true weight because your true weight is just mg. Right? But the apparent weight, what the scale says, is slightly different.
Okay.
Wondering if you could show me quickly if you can see anywhere that I went wrong on this one, because I only got
You did this one yesterday.
this. I know. And that was our group that did it.
Okay. All right.
I got both of these ones wrong, but I got that one right.
Well, that's good because you have to start with that one.
Mm-hmm.
So then you do, let's see. So that's 1. 2 times tension minus T.
The chain one.
Chain 1. Okay, so that's 3.
Yeah.
And you got, that should be right. So the difference here is that summation of the forces is 2t minus 2c1, but this system's accelerating. So this is accelerating.
Oh.
So that's why it's a little bit more complicated. So what is the acceleration of that compared to the acceleration of that?
Wouldn't it be the same?
Yes, because they're attached to a chain that doesn't stretch.
Right.
So the same. So you need to include 2t minus 2c1 is equal to mass times acceleration, which I don't, unless, oh, did you, is that this?
I don't know.
Okay, well, is that, okay, maybe that is that. So maybe you got that right then. So TT, that seems to be okay. So that's, well, I don't
It's
know,
like-
I'd have to check your math, but that seems to be right.
Yeah, I've already, I mean, as long as this is set up right, I've checked my math like 3 times. It was like 0.227, I think.
Okay.
So I'm close.
Yep.
And then this one's like 0.5 something.
Yeah, so this one though, that one is not accelerating, right? Because it's connected to the ceiling, which isn't accelerating. So that's the problem here.
Oh.
So that's wrong because it's not accelerating.
Okay.
You have this one set up right though, so let me take a look after class.
Okay, thanks.
All right, we ready to get back at it? Is that a no? All right, let's take a look at one of the classical examples involving centripetal acceleration, and that is taking a look at what happens when a car turns. All right, so in this example, we'll have, we're going to ask about what is the force due to friction. So you have a car turning, and the car turns because you turn the wheel, which turns the tires, which are in contact with the surface. And so you have friction between the tires and the surface. In order to turn, so we're actually, what is the force due to friction with the tires contacting the surface in order to turn a car that is traveling at 50 mph in a circle that has a radius of 20 meters. I have to give you the coefficient of static friction. We'll say that's 0.8, and the mass of the car is 1,000 kilograms. So that should probably be a question mark. Okay, so the picture looks like this. You have a car that is traveling like so, with some velocity. Yep. Increase the size. I can do that, I think. Been using that size for like 2 weeks, and now you tell me, come on. It's the color, I'm sorry. Again, you gotta let me know right away, because what I'm looking at and what you're looking at are not the same things, and I don't always remember that. Is that better? I can change the color too, since you mentioned it. Is that good enough? Geez, so demanding. All right, so here's a car that's traveling in a line with some velocity v, and we want to turn this car, we want it to go this way. All right, in a curve that has a radius of curvature of 20 meters. In order for it to curve in that direction, I must apply a force. Which direction is the force? Perpendicular, so that would be up down here, and then that way, and then this way. So yeah, perpendicular to the direction of motion. Good job. That means it's got to be accelerating perpendicular to the direction of motion. Okay, I'm going to draw another picture here because it's not completely obvious. So how do I draw my free body diagram? Well, let me ask you that. What does my free body diagram look like here? So tell me about the forces. So I have this force that's pointing up. I guess this sort of works, kind of. I guess we could use this one. The car is curving that way. It's not curving up into the air, though. That's why I don't like this drawing. So normal force and gravity, and that they kind of run into each other. So let me draw the picture of a car from behind, which I'm terrible at. So there's the car. And this car has a few different forces. So now this car is, it's curving to the left. So we're going to curve to the left like so. All right, so this car has a normal force acting on it, it has gravity acting on it, and it has the force due to friction acting on it, pointing to the left. Okay? Just so this is my free body diagram. That would have been hard to draw here with normal forces actually going up and things like that. So it's still just a Newton's second law problem. Nothing really new here. I want to know something about the force due to friction. So I want to know something about the x direction. So let's start with the x direction. Some of the forces in the x direction. There's only one. It's the force due to friction. I'm going to choose left to be positive x because I can do that. And I know it's accelerating, so my force due to friction is just equal to the x component of the acceleration, which is the only acceleration that I have. In the y direction, I've got something fairly straightforward. The normal force is balancing gravity. So the force normal is equal to just mg. Since we're not accelerating in the y direction, that's what we get. I'm sorry, this f sub x, that should be friction, of course. So this is the force due to friction is balancing mass times acceleration. So I have an equation that I can write for the force due to friction. Is this static friction or kinetic friction? I guess I wrote it down, didn't I? Coefficient of static friction. So it's sort of weird to think about, and the details aren't really all that important. But yeah, the tires are spinning, but the tires are spinning in a line straight forward. So the tires are spinning in the direction of motion. They're not spinning in the direction that I want to apply the force. So what's really causing us to move in that direction is static friction. Static friction is pushing against the tire. Okay? What happens if I am trying to exert a force that is greater than static friction? What happens to the car? Well, yeah, it's going to slide. That's when you skid, and you skid out of control, and it blows up, and you die. All right, so yeah, we want to make sure that when we're turning the car that we're not overpowering static friction. So what I'm looking for here is to basically see what happens to the car. So I'm trying not to be, I don't want to apply a force larger than static friction. The maximum force that I can apply is mu sub s times Fn. Remember, static friction has this maximum value. And that's got to be equal to mass times acceleration in the x direction. Now, since I'm making a curve, I'm assuming we're going to make a circle. Okay, so that acceleration, that's my centripetal acceleration. So if I expand the terms that I know the normal force, I know this acceleration term, so I can write down mu sub s times mass times gravity is equal to mass, and then centripetal acceleration is related to the speed of the car divided by the radius of curvature. So I'm just plugging in those values that I know all about. All right? Notice that my mass goes away, and if I'm solving for velocity or something like that, I can do so. But what I was asking for in the question, all I was asking for in the question was this term right here. What's the value of that? All right, and I can calculate that because I know I know my mass and my acceleration. So if I do that calculation, you would get, what did I get, 25 kilonewtons, I think? So this is just mv squared over r. Again, I'll write it down. Mass was 1,000 kilograms. Velocity was 50 miles per hour. Ballpark, what is 50 miles per hour in meters per second? Off the top of your head, if you were to guess. What is 50 miles per hour in meters per second? So you're listening to what I'm saying, 1/2. I did say 1/2. So it's about a factor of 2. So if you're converting from miles per hour to meters per second, then you multiply by 1/2. So it's a little bit less than half, so it's a little bit less than 25 meters per second. It's about 22 meters per second. So we have 1,000 times 22 meters per second squared divided by 20 meters, and that's going to give you something like 25 kilonewtons. Okay? So the question that I was asking is this mu sub s times Fn, is the force due to friction? Can I apply a force that large? Is that larger than, will that overcome static friction? So this is the actual force that I'm trying to apply by turning the car. This is the magnitude of the force that I need in order to go in that circle. That's 25 kilonewtons. So the maximum frictional force, that's equal to mu sub s times the normal force, which is equal to mu sub s times mass times gravity. If you do that calculation, you get, what did I say, 0.8 times 9.8 meters per second squared times the mass is 1,000. And so the maximum frictional force this is like 9,800 times 0.8, so something like, I didn't actually write this value down. It's something like 9,000, a little bit less than 9,000. 7,800, I was way off. So 7,800. So this is the maximum frictional force that I can apply, 7,800 newtons. In order to go in the circle, though, at the speed that I'm going, I need to apply 25 kilonewtons. So what this says is I'm not going to make the turn. All right? The force that I need to apply is much greater than the force that can hold me on the road. All right, so I'm going to try to turn the wheel, and I'm just going to slide because I'm going too fast. All right, so the follow-up question then is, okay, well, what is the maximum speed I can go to take this turn? All right, and so I was sort of going in this direction here. Now what I'm looking for is, okay, if I solve this equation for speed, that's the maximum speed that I can go at, because this is the maximum value of the frictional force. So if I solve for speed, I get v is equal to the square root of mu sub s times gravity times r. So that's equal to 0.8 times 9.8 meters per second squared times 20 meters. And if you solve that, you get something like 12.5 meters per second. All right, so that's the speed at which I have to take the turn in order to not go curving off into the great wide open or something like that. So here's my curve. It's got a radius of 20 meters. Here's my car. If I'm going at, whatever I said in the original question, if I'm going at 50 mph, so 22 meters per second, I'm going to end up over here. If I'm going at 12.5 meters per second, I'll be going just the right speed so that I make that turn. All right? Now, the numerical result is interesting, but more interesting is this result, our equation for velocity. If you want to take a turn very, very fast, what do you need to do? If you're in a race car, right? I thought of this problem a couple months ago when there's a roundabout by my house in Ann Arbor. There's these new roundabouts on the west side of town. And I was driving along, I was getting off the highway, and I like to take that round. I think it's great. They put it in there for us people that like to drive fast, because you go around, doing turns is fun going fast in a car. So, it was snowy out, it was icy out, and I observed there's some snow on the ground, so I observed this. Here's the roundabout, and here's the lane for traffic to go in, so like so. And you enter the roundabout from here, and then, I exit going this way. And I happened to notice that somebody else had tried this, and they decided that they would just go this way. All right, so they were able to go much faster than I was. So if you want to go as fast as you can going into this to take this turn, right, as fast as possible, you want to maximize the velocity. What do you have to do? Well, you have to maximize one of these things. Now, gravity is gravity. You can't really change that on the fly. There's no button in your car yet that allows you to change gravity. Mu sub s, that's a property of your tires and the road, so if you're going to change that, you got to get out and go get new tires. The only thing you can change is r. I have the choice when I'm coming into this turn. I can come into this turn and sort of, just basically follow the curve like so, or I can start on the outside and cut through the inside like so. The radius of curvature of this inside track is quite a bit greater than the radius of curvature of this track. So if I want to go really fast through this curve, I'm going to take the inside track where my radius of curvature is large. If anybody watches NASCAR or F1 racing or anything like that, you see this every time the cars take a curve. They start on the outside by the wall, and then they move inside down by the infield as they go through the apex of the turn. Right. Yeah?
Could you explain again the two numbers we calculated and how they relate to the problem, the 25 kilonewtons and the 7,800?
Sure. So I sort of did a poor job of explaining that because I was sort of going in a different direction. So let me sort of have a blank slate here. I'm asking sort of two things in the original question. I want to know, I basically asked, what is the maximum force that friction can apply, or that friction can handle? All right, so remember when we talked about static friction, all right, so the maximum force of static friction, which I've written out here in all its detail, is equal to mu sub s times the normal force. All right, remember static friction can, if I'm pushing just a little bit, static friction is just going to match that force up until some maximum, and that maximum is this value. All right, I want to know, how does that compare? That's when it starts moving. So once, in the example of the car, if I overcome this static frictional force, I stop turning. So at that point, I start sliding.
Okay.
So I want to know, how does that compare to the centripetal force required to go in a circle? Okay? That centripetal force required to go in a circle, well, that's just mass times a centripetal. And the value that I calculated for that using the velocity and the radius was that 25 kilonewtons. So this was, in our problem, that was the 25 kilonewtons. And this problem was the 7.8 kilonewtons.
Okay.
Yeah. So those are the two values, and I'm sorry I didn't explain that very clearly. So I'm just comparing the two forces. And so what this says is if I drive at that speed through a circle and try to make a circle of that radius, it's just not going to happen because the tires can't handle it. I'm going to go sliding off and crash into a light post or something. Okay? All right, so another thing that we can get from this equation, though, up here, so let me write it down over here. So we have V is equal to square root of mu sub s times g times r. Is what if this is on, so the value that I gave you of 0.8, that was sort of like dry road. What if we were on ice? So a coefficient for static friction for ice could be something like 0.2, ice with tires. So we lower the coefficient of static friction, which means we lower the velocity. So using the same values in our example, we're lowering the static friction by a factor of 4, which means we're lowering the velocity by a factor of 2, I think. Yeah, 6.3 meters per second. All right, so of course, physics, again, agrees with what you well know, that if you want to go around the same turn under icy conditions, you kind of have to slow down. Right, so nothing really surprising there, but at least it comes out in the math. Yep? This one? Yeah, so that came, I solved it using Newton's second law. So that was all this stuff right here. So it's just plugging in the force of friction is the only thing that's causing the acceleration. If I write down the normal force, which is just mass times gravity in this case, times static friction, that's equal to m times the centripetal acceleration, which is v squared over r. Solve for v, and you get this guy. Yeah?
And that equation with the velocity, is that only when the normal force equals the force of gravity?
Right. It's only when the normal force equals the force due to gravity. So I circled this just to highlight some of the intuition stuff that you guys have. Does this make sense with what we already know? But this is another case where I don't want you to just automatically go to this question or this solution. The proper steps for solving a problem like this is start from Newton's second law and get to that equation. Because if you have a different problem where you don't have the identical circumstances, this doesn't apply. All right? We could do such a problem. And that problem is if we throw in the additional wrinkle of adding some banking. All right, so now, again, if you watch race car driving, especially NASCAR, you see these guys that go to racetracks like Talladega where they have really steep banking. All right, so if you're taking a car and you're going, and they do this, of course, on the highway. If you're taking a car on the highway, you're getting on an off-ramp, the turn is banked a little bit, and that banking helps you go around in a circle. So we can look at the effect of banking on this car. So one of the questions that you could ask then is, this is sort of the classical question is, what is the angle? What is going on? I'm sorry? That's the back of the car. Yep, I'll draw that better in just a second. As soon as I get out of this. There we go. So I can ask, at what angle does a road have to be banked so touching many things, so that the car that has a mass equals 1,000 kilograms and a coefficient of static friction of 0.8 again, doesn't need to turn the wheel. And once again, in this case, v will just make it around 20 meters per second. And the radius of curvature now is 60 meters. All right, so given this stuff, the velocity of the car is coming into the turn at 20 meters per second. The turn has a radius of 60 meters, mass, coefficient of static friction. What angle does the road have to be banked so that I go in a circle? All right, so the free body diagram in this picture, all right, once again, like always, no, don't do that. Sorry, deleted it because I hit the wrong button. V equals 20, R equals 60 meters, mu equals 0.8, mass equals 1,000. There we go. All right, so what angle is the ramp at so that you can make this circle without friction? Without turning the wheels. So the free body diagram looks like this. We have a normal force, and we have gravity, right? Since we're not turning the wheels at all, there's no friction helping us go in a circle. So what we have here is a free body diagram that's a little bit simpler than we've dealt with in the past. So the next question is, though, what's the direction of acceleration? All right, I'm trying to go in a turn that goes to the right. So which direction am I accelerating in? Is it this way? No? Yes? Or is it this way? If I'm accelerating this way, eventually I'm going to crash into the ground, right? I don't want that. I want to stay at the same height along the banking. I just want to accelerate in a circle to the right. All right? So I don't want to crash. I don't want to end up in the ground. So it's not this bottom choice here. A little bit confusing. We're not going down the ramp at all. We're just going in a circle around the ramp. So I've drawn again from the back of the car, and we're making a turn that goes out sort of towards you and then back around towards me. Okay? Does everybody see that? That can be a little bit confusing. Leah, you had a question?
I have a question about what you said about friction.
So the question that I'm asking is, what is the angle of the ramp so that I don't need to turn the wheels to go around it? Just the banking is all that's making me go around it. Okay? What that means is since I'm not turning the wheels, there's no friction. There's no frictional force.
But you gave us a value for you.
I did, just to be tricky.
Oh.
Yeah, just to be tricky. It's because it's the same value from last time. All right? Don't be surprised if I do that sort of thing on the exam. Give you more stuff than you need. You guys are like, I hate you. Horrible. All right? If you can sort through all the stuff that you don't need, hey, welcome to the real world where you have all sorts of information, and trying to figure out what you need is really important. So, all right, so here's the problem. I only have two forces. I'm going to draw my axis to be up and to the right because my acceleration is to the right, so I like that direction. That means that I need to break up my normal force into its x and y components. So this is Fn sub x. This is Fn sub y. All right, the only force I have acting in the x direction is the normal force, the x component of the normal force. That's equal to mass times the acceleration of the car in the x direction. I don't know anything about that normal force, so I'm going to need the y direction. Some of the forces in the y tells me that the normal force in the y direction minus the force due to gravity is equal to 0 because we're not accelerating in the y direction. All right? If I give you this angle as theta, this is the angle between the original x-axis and the new x-axis. If I look at the angle between the original y-axis and the new y-axis, that's also theta. So the normal force times the sine of theta is equal to mass times gravity. That's my Newton's second law for the y direction. I solve for the normal force, which is what I need. mg divided by sine of theta. I'm going to use that in the x direction. So the summation of the forces in the x direction becomes the normal force times the cosine of theta now. And that's equal to mass times the acceleration in the x direction. We're going in a circle, so this is a centripetal acceleration. So I can write that as v squared over r. So anytime you say, hey, we're going in a circle, the acceleration vector, the resultant acceleration, that you say that's centripetal, that's just v squared over r. Okay, the result of the force is that I go in a circle. All right, so now I just plug in my f sub n right up in there. I get mg cosine of theta divided by sine of theta is equal to m times v squared over r. Once again, my masses go away. And I can solve for theta. So tangent of theta is equal to v squared divided by r. Well, yeah. Where did I lose? Oh, yeah, you're right. I lost gravity. Sorry about that. Thank you. Yeah, so the inverse tangent of theta is v squared over r. So tangent of theta equals...
Wait, shouldn't it be cotangent?
oh, that is a cotangent. I'm sorry. Thank you. So cotangent or 1 over, is that what you're saying? The inverse of tangent? Thanks. Sorry about that. Oh, no, it shouldn't be cotangent. I screwed up at the beginning.
Shouldn't
I've got these swapped. These swapped. That should be a cosine and that should be a sine. Why didn't you catch that? You slackers. I'm sorry, I'm having lots of issues today. Apparently our brains...
I have a question about how you define theta. If it's the angle between y and fn, then why are you using it to define the x and y components?
Because this is theta.
Oh,
By interior opposite angles, or I could draw a different triangle. I'm sorry. My son had his birthday today, so I guess pancakes this morning, my brain's not functioning right. All right, so this was theta, so if I'd done the trig right in the first place, I would have gotten the cosines and sines correct, which means that this would have been a sine, and this would have been a cosine, and then this would have been a tangent. Having all sorts of trouble today. All right, so it is the tangent. If you do the inverse tangent, you would get the solution. So v squared, if you do the inverse tangent of that, what you get, if you plug in your values, you should get something like 34.2 degrees. That's a heck of a slope to be driving a car around. But we're going pretty quick, 20 meters per second, you're trucking. So that's a classical problem. So I just want to point out, though, that again, we're just doing the same thing we've done a million times here. Draw the free body diagram, sum the forces in the x and the y direction. All we're doing now is we're sort of saying, hey, we could write this acceleration. Because we're going in a circle, we could write it in this tricky way where it's equal to v squared over r. All right, so we're sort of doing a little bit more than we've done, but really the entire picture is pretty close to being the same thing. Yeah, Lena, what's up?
How do we know that theta is in that corner?
All right, so just like before, what you always want to look for is you find the original axis. In this case, the original x-axis pointed like this. The new x-axis points like this. So if I go from the original to the new, the angle between them is theta. So if I find the original y-axis, which is like this, and I go to the new y-axis, which is this way, the angle between them is theta. All right? Always find the original and the new axes. The angle between them is theta. That's all there is to it. So let's say that I have, there's only so many ways I could draw it. There's only two ways. So if you actually just remember the two ways, that's another option. Okay, this angle is theta. All right, my original axis was like this. I'm rotating my axis now to be like this. All right, if I superimpose my axis here, it looks like the yay. All right, so which angle is theta? Now, in this picture, there are two choices. The only angle that we need to know is we need to know something about this down arrow. So either this is theta or this is theta. So the first thing is maybe to recognize, if you're having trouble with this, that it's a 50-50 shot. All right, it's either this one or it's either this one. So the question is, which one is it? All right, this is my original x-axis. This is my new x-axis. The angle between them is theta. Which is my original y-axis? This straight line, the y-axis goes up and down, okay? The original y-axis goes up and down, right? This line looks like this line. Which is my new y-axis? This one right here, all right? So the angle between the original and the new must be theta. All right, the original y-axis and the new y-axis. Not the original y-axis and the new x-axis, that's not right. All right, the original y-axis and the new y-axis. Figure this out. Either memorize that it's always this angle or something. I don't know. Or come see me after office hours if you're really not getting it, and we'll try to hammer it out somehow. Think of a new way to explain it. All right? That's the angle. All right, so we have this picture up here for a car. I'm going to do a slightly different picture. You're in an airplane. Airplanes look like this. If an airplane is turning, that's a pretty good airplane. What do you want? Put another circle here. Little thing. All right, so if an airplane's turning, you may have noticed that it banks. It goes like this. Why does it do that? Well, because the wings are the things that are keeping it upright. So if you just have an airplane that's in flight, these wings are applying forces. Those forces are balancing gravity so this thing doesn't fall to the ground and people aren't happy. All right, so if I bank the wings, now my forces, they point in this direction. Well, gravity still just points down. So I've got a net force applying in the x direction, right? The force in the y direction is still balanced by the upwards component of these two forces, but in the x direction, it's unbalanced. I'm out of equilibrium in the x direction. So that means there must be an acceleration in the x direction. So this thing is going to accelerate like this. This is the exact same picture as what we just talked about with the car. I could have just put a box here on a ramp. The picture is identical. Yeah, there's two forces, but I could just draw those as one force. Right? There's no difference. The math is exactly the same. Right? The force due to the wings, the x component is unbalanced because there's no other force. There's no force pointing off to the left somewhere. So the picture is identical. So this is how a plane is able to turn in the air. And you'll know this from being on a plane. All of a sudden when you're turning, you sort of fall to one side. So it's exactly the same, and you can do the exact same math to see this. All right? So I just want to point that out because you could do this problem in your sleep if you learn how to do the car banking problem. All right, does everybody see that? That was the airplane turning explanation in 1 minute. All right, in the last couple of minutes, I want to close up forces. All right, and I want to do so with a couple of conceptual questions that I like to ask. So the first one, I'm just going to draw a picture. You have some object. It's hooked up to a couple of strings. These are going over pulleys. So there's a force sort of in that direction. And then there's another force over a pulley in that direction at 45 degrees. Let's see, we're attaching this corner. We're attaching this corner to a spring. This is acting at 25 degrees. And then we're also pulling down with something called F sub P. Right? So 4 forces acting on this object. It's accelerating that in that direction. In what direction is the net force acting on that object? Leo, you're laughing? All right. My suggestion, I've heard lots of answers. My suggestion is to make sure you know the right answer to this before the exam. If you don't understand this, then you do not understand Newton's second law. All right? Newton's second law says this. This is the sum of the forces. In other words, that is the net force. Is equal to the mass times the acceleration. It's got to be equal in magnitude and direction. So if this thing's accelerating upwards, you damn well better believe the net force is up. All right? If I tell you that the mass is 10 kilograms, and the acceleration is 0.1 meter per second squared, what is the magnitude of the net force? 1 Newton, because F equals ma. Doesn't matter what each individual force is giving you. Who cares about these, what angle they're at? It doesn't matter. If I know the acceleration, I know the mass, and I know the net force. Now, every problem we've been doing has been asking, oh, what's the force due to friction, or what's the force due to the spring? Yeah, then you have to go through and you got to write out this term, and you got to break things up into the components and stuff like that. But if it's just talking about the net force, then you don't care about any of that. And that's what Newton's second law says. If it's accelerating, it's got to have a force acting on it in the same direction. All right? Make sure you're clear on that. Second conceptual question, this is dealing with a little bit more of circular motion. And it's a little bit more tricky. We have a slope that ends in a cliff. And we have person. Huh? Oh, have you seen this one? Okay, it is a ski jump. All right, it's a ski jump. All right, so this is a time sequence of the person going through the ski jump. All right, so at the first time here, this guy is speeding up. I'm going to tell you a little bit about it. Also speeding up, but he's entering his curve, so he's starting to curve. Here, speed is constant. Here, slowing down. And then there he's not on the slope anymore. All right? I want you to tell me, two things. I want you to tell me the direction of the acceleration and the direction of the velocity. All right, so let's do the velocity first. Velocity first, we'll do it in green. What's the direction of the velocity of this guy? So like this way? All right, what's the direction of velocity of this guy? Pretty much the same. This guy? Oh, I'm sorry. Same? This way? You mean he's going into the slope? That way? This guy? This guy? All right, good. Somewhere is the right answer. This is tricky because I didn't really tell you. He could be still going up and to the right. So somewhere between that and like this. So somewhere in there somewhere. We don't really know. We'll not worry about that one. Okay, good. So the direction of the velocity is perpendicular to the slope. And then after he leaves the slope, his velocity makes a parabola. I'm sorry, parallel. Did I say perpendicular? Yeah. That would be bad. It's parallel to the slope. Thank you. I'm just testing you. All right, so now the tricky one, the acceleration. What is the direction of the acceleration right here? Same as the velocity, speeding up. Right here, he's speeding up and he's starting to curve. What is the direction of velocity? Or the acceleration? He's starting to curve. Is he starting to curve? If his acceleration is in the direction of velocity, is he curving?
Should it start being perpendicular to the velocity?
Whoop. If he's got an acceleration in this direction, is he speeding up?
No, is it going down?
All right, which one is it? Huh? Is it this one or this one? Who says this one? Hands. Who says this one? Hands. Who says neither? Shane, why do you say neither? Shane is right. Why is it somewhere in between? Because he's both speeding up and curving. All right? If you're speeding up, that means your acceleration vector lies in a direction parallel to your velocity vector. But if you're curving, We just talked about this. It means your your acceleration lies perpendicular to the velocity. So I'm trying to make it a little bit more complicated on you guys. So he has both a centripetal acceleration and that the parallel thing that I talked about. Acceleration in the parallel direction. If you add those two together, you get the actual acceleration vector, which is up and to the right.
And you're saying that actual vector is perpendicular to the velocity?
This vector right here
Yeah.
is in the middle. This is perpendicular, this is along, so it's somewhere in the middle. Okay? So there's both a component perpendicular and parallel to the velocity. All right, because he's speeding up and curving. Right here, his speed is constant, so what's the direction of acceleration? Not zero. He's on a curve. He's got to be curving. If he's on a curve, he's curving. All right, his motion is making a circle, so all he has is centripetal acceleration. All right, he only has acceleration perpendicular to his motion. Over here, he's exiting the curve and slowing down. So here we're slowing down and we're going in a curve still. I know it's hard to see. We're sort of curving. Okay? So it lies in between the perpendicular and the parallel directions. Finally, over here, what direction is the acceleration? All right? Assuming no air resistance, it is straight down and it's gravity. Okay?